Good morning, everyone. Let's get started for today. I hope you all had a very, nice, quiet, reflective, re-energizing spring break. Yes, I can tell by your laughs that that's exactly what happened. Good. Awesome. Okay, so I want to first talk a little bit about assignment 2 and the unintended vulnerability. So this diagram that Eric made, right, shows how this process, how that files that you created, that files that you got, right, example.py and example.py.hash.gpg, right, how these were created. So on the server took the checksum of the example, right, into this example.py.hash, signed that with GPG with the secret key of the server, right, and then that was encrypted, and that's what you got, right? So the idea was you shouldn't be able to change anything in here because you don't have the secret key of the server, right? The way it should have worked, the server should check when you submit the hash, right? It should decrypt that with, so if it signed it with the secret key, then what should it decrypt it with? The public key, and only the public key, right? And if it used the public key, then it should decrypt that and compare the file that you sent checksum with the checksum in the file. If they match, then it executes the code. I made a mistake when I was setting up the server end because I imported into GPG the public key, right, which it needs to decrypt the signed private key. But I also imported the private key because I was thinking like, okay, both the keys should be in there, right? That's exactly how things should work. What I didn't realize is that GPG, when you tell it to decrypt something, it tries something very user-friendly where it says, well, I'll just try every single key you have, basically, until I can decrypt it, right? And so, if you took a new file, created a new hash, and you signed that with the public key, right, it would, on the server, it would use the private key to decrypt that and say, oh yeah, decryption went successful, check that they matched, and then would execute the file. So it was definitely unintended on my part. I didn't mean for that to happen, but it's kind of a cool example of how things can very easily, like the code, if you look at the code is fine, right? It's like decrypt it with GPG, and then check that the output was 0, which means it decrypted successfully. So I thought, okay, at that point, yeah, there's no way you could forge that because you don't have the private key. So I'll have to be more careful and probably automate how I set this assignment up in the future, right? So I don't accidentally have that key ring in there, or that the private key in the. But it seems ridiculous, right? Because that's how you'd want it to be. Because it's the server, it should have the private key in there. That's the only place the private key should ever be. Anyways, sorry, I was frustrated with myself. So the way that so there's a couple ways to do this, right? Another way was, well, you can create your own example.py, right? So how many different checksums are there? How long is the checksum?
2 to the 32, 32.
Yeah, 32 bits, right? So there's only 2 to the 32 possibilities, which is what, 4 billion? So that seems like a large number, right? But it's actually really short. So I think you said you were able to do 1 billion in 4 hours or something like that, like 1.7 billion?
Yeah, I think it ran. Yeah, it was 1.7 billion.
Yeah, I mean, and that's written in Python, right? This isn't even like an optimized C version. So that's actually one of the things I wanted you to kind of learn from this is A, the computers are really fast, right? So your computer can calculate checksum very, very quickly. So you can go and iterate through all possible checksum values, right, to find a collision. So that was one way. The other way, the way checksum works is it's basically a CRC32 hash, but it's that CRC32 hash hashed in with the length of the input file. So in CRC32 is I actually don't remember exactly how it works, but it's fairly simple, right? So you can actually iterate and try to break it, I don't know. I think it was Naveen wrote on the mailing list about how he did that, so that was very cool. So you can check that out. So any questions on this project? Everybody kind of get what the unintended vulnerability was and why it occurred? And I checked, there's no way to specify to GPG, only use this key, don't look at any other keys. You like cannot specify that on the command line. It's incredibly upsetting to me, yeah.
Did you find any other way to do this that anyone wasn't able to find?
Ooh, not that I know of. I guess I didn't, I haven't read through everyone's submission yet, so I don't know if somebody did something really crazy. Anybody do something really crazy that was not one of those 2 methods? Or 3 methods? Yeah.
I was trying, but if the assignment 2, part 2 was on the same server, same IP, using the assignment 1, part 1, that is data exploitation, I would have let my code run, and that code would ICMP ping my server, and I would write a receiver which would reformulate the secret.txt.
Yeah, they were running on separate machines for that reason specifically.
Yeah.
And even that one, part 2 was on a different CH root. So it was even on a different server internally and then inside a CH root. So that even if you broke out, you wouldn't be able to affect the rest of that server.
Okay.
And the file permissions were supposed to be set up pretty securely so that you couldn't mess with that original code, or you couldn't inject things into the GPG keyring or something like that. Cool. Anybody else do anything, try anything crazy? I mean, crazy that could have possibly worked, not just like.
So I figured out that that GPG actually tries to decrypt with any keys in the keyring. So I actually tried to set up my public key using assignment part 1 on the keyring, so that when I ran part 2, it would use my public key.
Yes. Different machines, and every submission is in its own CH root, and then gets totally blown away. So the next one is in a fresh CH root. Some of the changes you make are permanent, or should be. Cool. Okay, assignment 3 is going to be up on Wednesday. I had a little still setting things up because there's a lot of you, so I need to make sure we have enough resources, but we'll do that on Wednesday. So today I want to get back to command injection vulnerabilities, which is where we left off on Friday before break. Somebody refresh our memories, what's a command injection vulnerability?
Put something else to run.
Put something else to run. Actually, that's a very, actually a very good broad description, because command injection vulnerabilities literally come in all kinds of forms. Here we're specifically looking at what's called OS command injection vulnerabilities. So the idea is your application, right, doesn't want to implement every single possible functionality itself, right? So it wants to call out to external commands to do things, right? And so one of the ways that we do this, there's many different system calls. One is the library, the system call, which executes this command in a string by calling /bin/sh space-c string, right? So the -c says, hey, sh, run this command that's in this string, interpret this essentially as if this was typed into the command prompt. And so what this is going to do, it's going to open a process, it's going to create a pipe, it's going to fork this new process, and it's going to exec this new process, and then it's going to return all the results, the output of that results basically from this pipe, so we can read and write to it. So we kind of looked on Friday right before, but so how does sh or bash, how do they know what commands we type in? How do they know what's a command, what's the program, what's the argument? How does it know?
Splits it up based off the spaces in the given argument.
Yeah, right? So we know when we're on the command line, if we type in ls space something, right? We know that bash is going to interpret that as say, okay, that first part is ls. So use path to try to find a binary executable called ls somewhere in the path, and then exec that program, and the first, actually the 0th argument is going to be ls. The first argument is going to be that second thing that we passed in. And so bash is doing this parsing and actually calling those low-level system libraries for us. So what if we can control this string that gets passed in here? So what if this string comes from us?
We could run any command.
We can run any command, right? It's just as if we're at the command line of that system, right? We can run any command. So the basic idea of command injection vulnerabilities is if I can control this string, can I somehow trick bash or sh to execute whatever I want, right? So what could we do if we could execute, let's say, whatever string's in here? What are some of the malicious things we could do? Come on, you guys thinking evil. What are we talking about? Evil.
Read etc password or.
Yeah, you could read the etc password. So if you're remote, right, that'll tell you how many other, it'll tell you all the user accounts on the system. So you could maybe try to brute force either SSH, try to brute force their password from the outside. What else? What else could we do?
You can format.
We can what?
Format.
Format what? The system? Ooh, a little too evil. You gotta think like a virus, right? Like in biology, right? A virus doesn't want to kill its host first. It wants to like get them sick so they spread the germs and then maybe kill them later, right? But, so we're kind of the same way, right? We maybe, I mean, it depends on what it is, right? If it's, I don't know, maybe we make like a bank transfer out of our account and then while that's still pending, we like kill that machine so there's no record of that, so now we have the money. Yeah, that could be an instance where we want to like kill a machine, right? Yeah, so we can do rm-rf/, right, which will try to delete everything on this computer that this program can or that this, whoever's running the system command, whatever privileges that user has, will delete all their files. It'll be pretty cool. But what if we can't control the whole string? Right, then what can we do? So let's look at an example. So let's say we have our C code, this main function, and so we have some command that's, so this is a buffer of characters, right? 10,024 characters. And we're gonna printf, we're gonna use SN printf, so what's S, the S in the printf mean?
String.
String, not secure. Yeah, another instance where terrible naming.
Yes.
So this means we're going to output to a string, right? What does printf normally output to? Standard out, right? So file descriptor 1, right, is another way to think about that. So what's the N mean? Yeah, limit the output. So this says the N means only output at most 1,024 characters, right? So it doesn't. So it's going to do this printf. It's going to output the result of this printf into the string buffer CMD. And it's going to do this only 1024 characters. We'll see exactly why it's important next. But for here, we know, okay, this buffer is only 1024, so we know we should never write any more data than that. So this is the printf directive. So what's the printf going to do here? So what is the programmer trying to do? Is it legitimate? Is this like a normal thing? I see some nodding. What are you nodding for?
Sure.
Yeah.
I mean, read different log files. So
Yeah. It's a program to read different log files, right? The user can specify what log file they want to write, and you know, maybe this is running a setuid, right? Because maybe log files are protected by the user, but hey, you know, we want to give a way for people to read their log files, maybe not write to them, but read their log files, right? So this is going to create in CMD, it's going to be the result is going to be cat space /var/log/ whatever the user types in, right? And then because we're really good programmers, right, we know that C strings have to end with a 0. So here we're setting the last thing in command, or the 1023rd byte, the last byte to be 0. So we're making sure we're null terminating this string. And then we're going to output system calling it with this command. Right? Seems reasonable. This is how we would write it. So, is it secure? So, is there a command injection vulnerability here? So A, what can we, the attacker, control?
What location we're going to be reading from?
Yeah, so we can A, control what location we're going to be reading from, right? So what can we use, maybe that we've already talked about, to be able to, can we read arbitrary files with this?
I mean, we can use directory traversal.
Yes, we can use directory traversal, right? We can use dots to output any file on the system, right? So we can do ///. That'll allow us to output any file on the system. That's pretty cool. But we don't control this whole string, right? It's not like we're passing argv1 directly into the system, right? So we don't control this whole string. So can we get this to execute arbitrary code that we want?
Yeah, can't you just do a semicolon and then another?
Can't you do a semicolon? What's a semicolon mean?
It means to run the command before and then after that run the next command after.
Yeah, but where is that? Who's doing this semicolon nonsense? Is that Linux that's doing it? Is that the operating system? Where does that come from? Where does that behavior come from?
Oh.
Yeah.
From Bash?
From Bash, right? Yeah. The shell, the system. Underneath in system, right, it does the equivalent of bin sh-c with that string that you pass in. So sh is right? One of the ways on the command line that you can execute multiple commands, right, is with a semicolon. Right? Which means first execute this command, then execute this command. So what if, let's say, you guys want to read, let's say, I don't know, the etc shadow file? Yeah? Could be fun. Okay, so what if we run this program? So what string would we pass in to output the etc shadow file? Using a semicolon. Yeah. You have to be perfect. It's fine.
Oh, some variable which is maybe one string, semicolon, cat /etc / that's what.
Yeah, so we're going to want to execute this program, right? And then for argv1, we're going to put something in there. So we may want spaces in there, so we're going to put that in double quotes, right? And so we can just output kind of anything, whatever we want, foo, and then semicolon, and then a space, and then cat /etc shadow, right? So just exactly as if on the command line we said cat /var/log/foo semicolon cat /etc shadow, exactly like how Bash is parsing our command lines when we're on the command prompt. This is exactly what system is doing. What sh is doing is parsing this string. So it's going to say, hey, log foo. It's going to say file not found, right? Because this first part isn't found. And then it's going to execute that next part and give us the root, whatever etc shadow is, right? And it'll keep going. So what are some of the other ways that we can execute? So what if this programmer's like, aha, I've taken a security class. I know that semicolons are bad. So I'm going to filter out all semicolons, replace them with empty, with nothing. Does that fix this vulnerability?
No, there's and you can use.
There's and. So what does and do?
It executes the first command. If that returns a success, only then will it execute.
Yeah, so the double ampersand means execute this, and then afterwards that's successful, execute the other thing. What else?
Pipe?
Pipe?
Yeah.
Yeah, pipe is output this program and then execute the thing after the pipe and make the standard input of that the standard output of the other one.
You use, I think it's /b, but basically create backspaces. So escape sequence, you backspace over the original command and then write the new command.
Backspaces, I don't know if they would interpret that because
This sprintf probably would.
I think it treats that as a byte. Oh, it may, if it is using sprintf.
I don't know if it still works. I know that it used to work.
Yeah, there probably are cases where it does work. I actually don't know. That'd be really interesting to look at.
Yes,
That's
so
cool.
definitely.
Yeah, so if we could get printf to kind of delete these characters, right? Then we could just use the backspace character allowed us to do that, right? We could put in backspaces to be here and then replace this whole string with whatever we want. And then we're not even using semicolons or ampersands. What else? Yeah.
Could we place a symbolic link at that parent directory folder?
Ooh, yeah, so we could put, because we control this, right? If we can control that, then we could put a symbolic link to make it output any other file. Yeah. What about other ways we can get code to execute?
Encoding.
What was that?
If we encode the semicolon into something like URL encoding or something.
What encoding would you use?
Any kind of encoding. Simplest is URL encoding.
URL
if
encoding.
the server is interpreting only semicolon and not the encoded version of it, then it might execute it decoding.
No, bash
But
is
will
running.
it execute it, right? That's the question, is will bash execute a percent encoded
Yes.
semicolon? So I would say no, right? Because bash predates URLs. So
What
I'd
if
say
it's downloading a file, or what's called, yeah, like a software that will allow us to have more access. Like if you have a server send something like wget and
Mhm.
some C program and then compile it through there.
Wait, say that again?
We can download a C
Oh.
file, I guess.
Oh yeah, so once we're here, right, once we get arbitrary execution, we can do whatever we want. Yeah, we can download a C file just like the Morris worm did, right? It downloaded a C file, compiled that C file, just ran code. We could, once we have access here, we can try to create a new user on the system, change keys around, change passwords, basically use this to do whatever we want. Yeah, we could create like a reverse shell that'll come back to us, and so we can type in commands if we want to do it more interactively. But for bash, so what are all the other ways? So we talked about ampersands, double ampersands, we talked about semicolons. What are some other ways? So how would we find out? Yeah.
Could you use control, like control M or a control character that would pass that in through ASCII or
Maybe, I don't know.
hard enter?
Yeah, it would be, those could be what bash reads in from standard in. It may be that it's, when it reads those characters it does something, but it may not be if putting them in the command. Yeah, where would you find out about that? What was that?
In the documentation.
Yeah, in the bash documentation, right? So let's do that now. Alright. Man, man sh, which is linked to bash. Let's see. So invocation, so we can see this is very long. So we can see shell grammar, so simple commands. A command is a sequence of optional variable assignments. So we have pipes, so we talk about pipes. And interesting, I didn't realize this, right? But a pipe can be specified by pipe or a pipe and an ampersand. Right? That's kind of interesting. A list, here we go. A list is a sequence of one or more pipelines separated by one of the operators, semicolon, so single ampersand, right? So if they filtered out double ampersand, we could use a single ampersand. Or the double bar, right? So what's two bars? Or, right? So that's another way we can get another process to be executed. Let's see. Yeah, so the single, what's the single ampersand do?
Runs in the background.
Runs in the background, which could be nice, right? Then we may not get the output, right? But hey, at least it's still running. So here it shows all the things. So we can do compound commands. Let's see, there we go. So we may be able to use the double brackets to do expressions. Now we're getting kind of crazy. So where's, I can't remember the name of that. Actually this is an important thing. So we can define new functions, which is kind of interesting, which we'll see in a second. Interesting, I didn't know this. A co-process? See, you learn something new just by skimming through documentation. Okay, there's another one. What am I looking for? Quoting. So yeah, maybe /b would do something. That could be really interesting. Parameters. There we go. Okay. Command substitution, right? Does anybody use backticks in bash? Right, so backticks is execute this command and then inside this argument put the result of that command there. Right, so we could use this too. We could use backticks to execute whatever we want. And the equivalent to backticks is the $, left paren and then right paren. Right, so anything in here is going to be interpreted as a command. So really, what's happening here, right, is that bash is taking in this string that the user gave it, and it's parsing it, trying to interpret what does the user want to happen, right? And we can see that the bash language is crazy and very long, right? And has all these cases of different things that it will do or not do. Yeah, so let's see. Arithmetic, process substitution, all kinds of cool stuff. Oops, that's not where we are. Yay. And it's not, is it dark?
No.
Okay. So the root cause here, right, is that what did the developer want to have happen here?
Just read long lines.
What program did the developer want to be executed? Cat, the cat program, right? And what was the first argument that the developer wanted to pass to that cat program?
The name of the log file.
Yes, the name of the log file, which happened to include user input, right? So did the developer intend for semicolons to be used to execute more commands? No, right? And so this is the main problem, is that essentially the developer is concatenating strings together, right? So the first string here, so it's concatenating a string that it wants, right? Cat space var log, and then concatenating that with the user input to create a new string that it then passes to bash and says, hey bash, figure out what I want to do from this, right? Whereas the developer knows exactly what program and how many arguments they want to pass to that program, right? So really using system in this context with user input is incredibly unsafe, because so what the programmer should do is use a different function where they can specify like one of the exec commands and say, okay, I want you to execute this program, and these are the arguments of this program. And that way, no matter what the user can do here, right, extend this string, change this string, that's only going to be passed as an argument to the cat program, right? Bash is not doing reinterpretation of that string. And so this simple vulnerability manifests itself over and over again, and even recently. So anybody remember the Shellshock vulnerability? So back in September 2014, there was a huge uproar in the security community because there was a bug announced in Bash based on how it processed its environment variables. So, as we've seen, right, when processes are invoked, they inherit the environment of their calling process, right? And so, in Bash, you can do this as well, right? Bash can invoke new Bash instances and have new environments. And this is kind of nice because you can pass variables to your sub-children, sub-processes. It turns out that Bash has this crazy little-known usage to where you can pass a function definition into your child Bash, right? Which seems legitimate. That seems like something that could be useful in some circumstances. And so what you do is you create a new environment variable, and that environment variable you start with left paren and right paren, and then everything after that is a function definition. So by itself, that's fine, but what Bash does is, when Bash is started, it goes through all the environment variables, looks for any environment variables that has a value that starts with these parens, and then will execute that code there in order to create that function. Right? Makes sense. That's how you create this function. Who controls the environment variables? Yeah, the attacker can, right? They're user controlled, right? And what makes this so, you can put commands in the function definition to execute arbitrary code. So you can get it to execute arbitrary code by creating these function definitions. So there's a way to, for instance, anybody, hopefully a lot of you use Git or GitHub, right? So when you pull down a repository from GitHub, oftentimes you're actually using, so you've uploaded your SSH key, right? So they're giving you SSH access to one of their machines.
Right.
Doesn't that seem crazy? Big company, lots of people source code, they just give you SSH access to their machines. So has anybody tried to SSH into a GitHub machine? If I say GitLab, I mean GitHub. Does it work? Kind of, yeah. So actually there's a way in SSH to restrict the access that an account has when they SSH to your machine. You can even restrict it to say you're only allowed to execute this specific command. So in this way, they only allow you to execute whatever the get server command is. So using this, you can actually, if you have, so SSH, when it gets an incoming connection, it creates a variable in the environment called SSH original command. So if you, and that value of that command is then created by the attacker. So they could create this SSH original command with the parentheses and then arbitrary code, and now they can break out of this and execute arbitrary code here. So you would try to execute something like this, and this would get executed on the system. Because the SSH, right, puts this into an environment variable and then calls a program, right? Because that should be safe to take user input, create an environment variable, and then just call a program. But this cat command is going to be output, right? So you're breaking out of there. But if this was just the case, it probably wouldn't have been such a big vulnerability. The big problem was, so we're actually going to see when we get to web, CGI web applications, right? Accept any user input. So anybody maybe who's taking my 591 class, remember, how are variables passed into CGI web applications? Through the URL is how it gets in, but how does it get into your program, the CGI program? What was that? Yes, post or get is how it gets in, but how does that get passed into your program?
Command parameters.
Not quite command parameters, close.
Headers?
Headers, no, not quite. Although I think you do get the headers in your program, but. So a CGI web application is just a program. It executes. And it was created sometime in the late 90s, I want to say. So it was intended to be very broad. So you could write literally a web application in any language that you could make a binary executable. And so one of the easiest ways to pass in arguments to a program is to use the environment. So it defines specific variables. Like if you want to get the URL, you have to get the environment variable called, I actually don't remember what it's called, like URI or something like that, or URI location. It's actually a list of about 20. So, doing this, right, and when the web server is invoking your CGI program, it's essentially instantiating a new version of bash, which is then going to look at all the environment variables, see if there's any with these parentheses, and then execute that function definition. So you could get remote code execution on a program just by issuing a single web request, which is why this was such a big problem and a big vulnerability. Through a web request, you don't have to be, even if that web request is going to give you a 404 not found, or well, maybe a 404 wouldn't work, but like a not authorized request, right? Even if you're not authorized for that, it's still, that CGI application has to execute to tell you you're not authorized, which means it's going to parse your function that you gave it and execute your arbitrary code.
Right.
So huge problem. There's a huge chunk of the web that was vulnerable to this. All right, so what do we learn? Yeah.
Never take user input if you can.
Never take user input if you can. Yeah. It's kind of analogous to the most secure computer is one that's like unplugged, locked in a room, right? No access. It's very easy to make something secure like that. Yeah. But if you can help it, right? If you know what log file you want to be output, just write it, right? Don't make the user put it. What else? Anything else?
Try to whitelist and not blacklist. Like, so what I mean is that don't try to prevent all the possible ways a user can give bad input, but check for only the correct ways that you are expecting.
Right, so that would be one defense, right? Is or one layer, just kind of like as we said, okay, block semicolons. Well, then I'm going to use double ampersand. Well, block all ampersands. Okay, then I use bars. Okay, block bars too. Okay, then I use ticks. Okay, block ticks, and then I can use $ parentheses, right? Like there's probably still other things that you can use. Yeah.
Well, in that case, you wanted a file length, so you could at least limit it based on what a file
Exactly.
Absolutely, right? So we should
Regex
be
for
A through Z, uppercase, lowercase, digits. What about spaces
underscores.
though?
Spaces would come with a slash probably.
Can we do spaces? Yeah, so but if we allow spaces, right, then they could pass additional arguments to cat to output additional files. Right?
Make sure these spaces has a backslash before it.
Yeah, so maybe you could do that transformation, right? To sanitize it by replacing all spaces with backslashes. We still get into tricky issues. And then we have the, directory traversal attacks, right? So we have to worry about all the dot dots. Yeah.
I don't know the term, but you're using a command that's too powerful. So maybe there's a more effective command to use than just system call to cat versus.
Yeah, so that's actually a good point, right? So we just want to output this file. Well, how do you output files in C? Or how do you just read the file, you open the file, and you output it, right? So you can actually do that functionality yourself. But there's probably less room for error. And on that same note, right? So we saw that system, and if you look at popen, it works the same way, right? They are taking that string and reparsing, Bash is parsing that to figure out exactly what you mean by what number of arguments you want and everything. So we should use alternatives. So we should use the exec system call, which allows us to specify exactly how many arguments and what those arguments are, right? So if we were to use exec VE, right, then what we pass in as argv1 there is only going to get to that program as argv1. It's never going to be interpreted as, no matter what semicolons or whatever junk we put in there, it's only going to go as the argument to that function. And it's not going to be interpreted. So yeah, it's in a sense, these programs are like the system call is actually very flexible and powerful, right? It does some cool stuff for us, and you can do very cool commands. The problem is once you allow the attackers to influence what commands you execute, they can usually trick it into executing arbitrary things. And yeah, so we should always be thinking about sanitizing, right, the user input. Users are dirty, right? So we need to make sure we sanitize all their input. So another thing, right, and this is going to come up again when we look at SQL injection, cross-site scripting, right? When we get to this system call, does system know what part of this input string came from the developer and what came from the user? No, right? Whereas this string this part came from the developer, right? Cat space /var /log. So that should be safe, right? The developer is doing it. It should be safe. But it's that other part at the end that's unsafe, right? But from system's perspective, right? And once it gets to sh, system just calls /bin/sh-c with that parameter. So when it gets to sh has no idea where these bytes came from, right? They could come from the user, they could come from the network, it could come from a file, it could come from a hard-coded string, right? So this is another problem is, you think about it, so yeah, okay, I won't get into it too much. We'll revisit this again, this concept. Okay. So now we get into kind of the kind of root, or one of the coolest, oldest vulnerabilities in binary applications. Something we saw the Morris worm used buffer overflow of vulnerabilities, and there's still, these types of overflows are still prevalent today in today's binary systems. So this is why it's really important to study and learn these things so we can understand what kinds of essentially memory corruption vulnerabilities can happen. So these are, as we'll see, I think of them separately than what we looked at before. So we looked at kind of how to manipulate file access, right, by using directory traversal attacks and symlinks. We saw the command injection, which we're able to influence some other program to execute arbitrary commands on our behalf. This class of vulnerabilities is really about the attacker being able to change memory and alter the execution of our program itself. So we're going to look at exactly how this happens. So what happens when you copy like one buffer to another in like C. What are buffers in C and C++? Just arrays? Right? So what's an array?
Sort of contiguous memory.
Yeah, just contiguous set of memory, right? How do we know the size of that array? What was that?
Find the length and divided by the size of the each.
How do we specify the length? Who specifies the length?
The n byte minus the starting byte plus 1.
What was that?
When you declare the variable.
Yeah, so right, we saw it on that last example. We declared a command that's 1024. So either it's at compile time where the programmer says, this is an array of characters, it's only 1024 bytes. What's the other way we can allocate memory in our program? Malloc, right? But then how do we specify the size of that? We pass it into the command, right? Malloc takes in a number of bytes and returns the address of those bytes in memory, right? So we could call malloc with 1024, and that'll give us 1024 bytes that we can do whatever we want with. So then what about when we write to an array? Who checks that we're not writing more than 1024 bytes? No one, right? We have to, the programmer has to, right? When you're writing Java, Java internally stores the length of the arrays, right? And so every time you write to an array, when you say, hey, write to index blank, it's checking, is blank greater than the length of the array? If it is, then it stops that, right? Blocks that write. Is anybody checking the length of your indexes where you're writing to in C? No, absolutely not, right? And I mean, I guess it makes sense historically because if you're checking every time you're doing an array write, that has a performance cost. Yeah, exactly, or a performance hit, right? Because you're slowing your program down by having an if condition every time you write into memory based on an array, which could be a lot, right? How many times you iterate over an array doing something to an array. So if you're iterating over an array of 1024, right? Every time you write to that array, or read from, right? Every time you write or read, you have to check that length. And so C and C++ applications don't have boundary checking. So they don't check the bounds of the arrays that get written to. And so this leads to, as we'll see, basically overflows are writing more than the size of that buffer, the allocated memory for that buffer. So once you're able to do that, we'll see how you can control the program's execution. These are very tricky attacks because they're very architecture and operating system even version dependent. So these will typically, a specific exploit will only work on a specific version of the operating system with a specific compiled version. They're very cool because they can be executed both locally while we're on the system, but also sometimes externally if they use external user input, which can be super cool. And we'll see that they really, our goal as an attacker is to modify the control of the application to get it to execute whatever code we want to do. We can also, a new type of these attacks that are happening is we can also change the data of the program, right? So if the program has a bit that says whether we're an authorized user or not, right? And that's at 0, and we're able to overflow some buffer to change that to 1. Now we're an authorized user, right? We've tricked that program. So there's actually a lot of work on automating this process of doing these buffer overflow attacks, which is super cool. But we're going to be doing this by hand. It's really important that you learn how to do that. And so there's actually a lot of research into automatically finding these vulnerabilities, automatically preventing them, and developing detection mechanisms. So there's this arms race where we develop we say, okay, they're exploiting the programs like this. So now let's do a new type of defense. Let's add, I don't know, stack canaries or ASLR or whatever thing you've heard of as defense, as we'll talk about. let's do that, and then people do that. And the attackers are very smart, so they get smarter, and they say, oh, but now I can do this other thing using this same vulnerability. And so the defenders keep trying to go up and up, but attackers have a financial and, I guess, eliteness incentive to develop cool new attacks. So attacks always are getting better, and now they're incredibly complicated. And actually, so some of this research has gone into actual commodity operating systems that's on all of your phones, devices, and operating systems. All right, so to understand this, we first have to understand the stack. So what's a stack generally? Data structures, stack. Yeah, last in, first out, right? Push things on, pop things off. What is it used on for x86 for programs?
Storing return values and things like that.
Yeah, so it's essentially, I like to think of it as scratch memory for functions, right? So each function, their local variables are stored on the stack, parameters are stored on the stack, right? And this is how we can have recursive function calls, right? So I hope, I'm going to go through this fairly quickly because this is review from my undergrad 340 class. Because we talk about the stack there to understand exactly how local variables are laid out in memory. So this is where this comes from. So all my stacks start at high memory addresses and grow down, right? Just like we saw the ELF, the process space, right? Starts at high memory and goes down. That's completely arbitrary, right? You can start at low memory and grow up, but I don't know, whatever reason I got stuck in this way, so this is the way I'm gonna do it forever, and so will you, so. Or at least for this class. Okay. So functions can push registers or values onto the stack or pop the values from the stack into the registers. So this gets back into x86. So we're gonna look at actual x86 code. So in x86, right, ESP points the address of the top of the stack or the bottom if it's growing down, right? So logically it's the top because when you pop things off, it's gonna move. And when you add things, it's gonna move, right? So the instruction push EAX first decrements the stack pointer, right, which is going to move it down in our thing because we're going to go from high to low. It's going to decrement it and then store the value of EAX at that location. And conversely, pop works exactly the same way. So it's going to take that value that's at the address pointed to by ESP, put it into EAX, and then increment the stack pointer by 4. So let's look at what this looks like. So we have our stack at the top, we have low memory at the bottom, and it's just a bunch of bytes, right? So there's a bunch of stuff in here. So the stack pointers, let's say here at hex 10,000, below the stack pointer, right, is garbage, right? It has absolutely no meaning to our program. Obviously, if we saw if we go down far enough, we'll hit the heap, but for now, considering just the stack, right? Anything below the stack pointer means nothing. So if we have a function like push EAX, pop EBX, if we have registers, if the value hex A is in EAX and 0 is in EBX, and the stack pointer, right, has the value 10,000 hex, right? So the only way we know this, that 10,000, so the way we know that this pointer here to the stack, right, the top of the stack, is here is because there is the value 10,000 hex in ESP, right? And so if we said the stack started somewhere else, then there must be a different value in ESP. So this pointer, this arrow just represents the current, where ESP is currently pointing. So if we do push EAX, right, to execute that instruction, what's going to happen is ESP is going to be decremented by 4. So it's going to be FFFC, EAX, so it's going to move down, right? And then EAX, which is, what's this, 10, decimal 10, so hex A, that's going to be copied and put into there. And now if we do pop EBP, right, we're going to say, okay, take whatever ESP points to, whatever the value is there, which is hex A, copy that into EBX, and then increment the stack pointer by 4, which means it's going to point to here. And so essentially we've been able to copy the value in EAX to EVX by using the stack. Right? Now we know that at FFFC, there's now the value 10. Right? We know that, but it's garbage to our program, right? At this point, it's essentially been deallocated. We don't really care what that value is. Okay, so thanks for being patient. All right, on Wednesday we're going to finish all of this background material so we can understand exactly the stack and what's happening so that we can understand buffer overflow vulnerabilities.